the magnetic field changing. Those are sort of your typical ones. Then this one, the sliding rod, is a kind of a different one. How about a rotating rod? This is kind of unusual. Imagine this rod is rotating about its center. Let's say the length of the rod is 40 centimeters again. Let's say it's rotating counterclockwise with a RPM, 500 RPM. I can say calculate the, let's say the resistance of the rod is 6 ohms. I can say calculate the EMF induced in the rod, EMF induced, and the current and its direction, Calculate the EMF induced and the current and its direction in this rod. And of course, I'm assuming that in this region, there's a B field, let's say either out of the board or into the board. Let's say, so the whole region is full of magnetic field, let's say out of the board, and let's say the magnitude is 2 Teslas again. Now this is kind of weird because usually you would think you need a full loop, right? You need a full loop or something to make a loop, but it doesn't actually have to be. You could kind of imagine as if there is, this is going like this, and ask yourself, how would nature want to act here? What direction current should be induced in here such that the force of the magnetic field on that current would fight against its motion, you see? That's how I would visualize the current and its direction. So remember what I just told you? If there is a current going from the outer edge of the rod to the center of the rod, right, like that, then what would be the force of that, force of the magnetic field on that? So if there's a magnetic field coming out of the board, then you say I crossed into B, then the B field, the force on the rod is this way. But that would actually help the rod rotate counterclockwise. So we got to try to fight against that, you see? So the current should be headed that way, actually, you see? So the current should be headed from radially outward. So this way, such that if I do the cross product, I cross into B, the force on the rod will be opposite the direction of its motion. So to handle direction, that's the easiest way on this kind of a problem. Just say the current's going to be radially outward. The direction, radially outward. Okay, so to do the magnitude of the EMF and the I, you kind of can visualize a little area here, like this, right? Or you could say dA, so you could say the EMF created is negative N B dA dt, right? And then you have here, the loop is just one because it's just one loop here. And then the B is into the, is it out of the board? Okay, then if it's out of the board, it's positive 2. And then what's the area of, if this is here, theta, what's the area of arc length here? Let's see here, the area of this, isn't it? This is radius r, theta, it's, is it half base times the height? Yeah, it should be half times the base times the height, which is r, and then the base is s, and that's equal to r theta. So is the equation for area half r squared theta for a segment of a pie. That should be the area, right? Because the way that to test this equation is to put theta is 2 pi, right? Then that would be the area of a circle. If I put the area is half r squared 2 pi, then that cancels that. Oh, there you go, pi r squared. So this, I just derived the equation for the area of a segment of a pie. So now I'm going to take the derivative of that. The derivative of this, dA dt, so the radius is not changing, half is not changing, so half r squared, and then you've got d theta dt. Okay. Yep, you got it. So then that's the EMF that's induced. There you have it. So we have here 2 cancels, negative r is going to be 0.4 squared, and then the theta dt is let's see, 500 RPM. Remember yesterday I showed you how to change that. So revolutions per minute, 500 RPM. So then we could say 1 minute is 60 seconds. Now, if I want to change it, the theta dt, I want it radians per second. So I can say 1 revolution is 2 pi rads. Okay, then that will make it in radians per second. So then I have here 500 divided by 60 times 2 times pi. Okay, so the theta dt is 52.359877 radians per second. 78 radians per second. And now this times this, and that should give you the voltage in volts. Yep. So then you have here 52.349878 times 0.4 squared. And it's actually pretty big. The EMF is 8.38 volts. So that means literally that, remember, we determined that the current is flowing in which direction? Radially outward. That literally means between this end and this end of the rod. Remember, current likes to flow towards lower voltage. That means this end of the rod is at a higher voltage. It's 8.38 volts. And then this end of the rod is at 0 volts. You see? So that's what it means to say that there's an induced EMF in the rod due to the rotation of the rod. That's really weird. Even though the rod doesn't really make a loop itself, but it kind of makes a loop because as it's going this way, it sweeps out an area. You see? It sweeps out an area, so it's kind of making, if you think about it, it's making a loop like this with itself. You see? So the current is flowing outward, and then the magnitude of the current is going to be the EMF over the radius, over the resistance, right? This is the resistance, so then just divide this by 6. .40 amps. So that's actually a pretty noticeable current. So just by having a rod just going like that in a magnetic field, you're creating current in the rod.